Hi everybody, I really appreciate you coming here and having an interest in the topic of ZK and participating in this privacy related program, Brew. I think it's interesting to see how this program, basically how it will run. And yeah, I think it's important topics, important accents and so on. So today my goal is to basically give an introduction to ZK to you from kind of more builder perspective. So this is, I would say, it would be more builder oriented. So for example, I will not go too much into the mathematics of how it works, even though it's really interesting and exciting, but maybe it's not the right audience. Also, I will be, I will be putting some examples as well. We will see later what happens. And as Gentin already said, we'll have a workshop to actually get our hands on some ZK. And yeah, so I expect, maybe I will start with who I am. So my name is Sergey. I'm a ZK researcher at L2Beat. I will be showing what L2Beat is sometimes during the presentation. So my background is mathematics. I have a PhD in mathematics. I work in blockchain for 4 years now, and ZK has been a very interesting topic for me for the privacy reasons, and I'm quite excited about decentralization, about decentralized technology, private technology, and the technical side of cryptography. So that's why I'm really interested in this topic. And yeah, that's why I will be also happy to tell you about this today. Yeah, by the way, I have posted the links to the slides and the repo for workshop in the here in the matrix chat in resources. So you can find the link to the slides later, and you can check out all the links that are in the presentation. Okay, so here is bit of an overview of what we're doing. As I said, we'll have a presentation and the workshop. So you have to understand that ZK is a big topic. There are so many different aspects. I inevitably have to pick some and leave something out for this presentation. So I conceptually broken down the presentation in 2 parts, starting with more gentle introduction for people who maybe don't know so much yet, and the second part will be maybe a bit, let's see. Actually, I don't think it's too much more involved, but just to say, if you find, for example, part 1 to be a bit boring, maybe part 2 will contain some new information for you. So let's see. Yeah, I also, we will have a couple of breaks to digest, and especially one before workshop to set everything up. And more precisely, what I will be talking about in the slides. I will do some intro. I will cover a couple of examples of using ZK technology, starting with ZK rollups. Then also continue with some more privacy-oriented examples, taking the ZK ID one, and next I will explain in the second part different architectures, speak a bit about ZK VMs, and I will give a couple of links to some materials so you can explore further. And my last example will be about a protocol to basically anonymously vote in DAOs, continuing these examples in privacy. So yeah, the plan is to sprinkle up some examples to keep it maybe a bit more practical, but also explain step by step what's going on. Yeah, so this is the plan, and let's begin. So I will start with the very basics of ZK, and maybe one sentence what ZK is, you can see on the slides. This is a cryptography that allows attesting to some computation. And this could have some private inputs. So my first question to the audience is, what is computation? Can somebody explain to me what this is? Yes, Nate?
A series of steps to transform information from one state into another.
Yeah. Or what you have to.
Anything what can be expressed with Turing machine.
Yeah, that's also good explanation. So yeah, basically when I say computation here is a Turing machine is a step of computation. This is some program that runs, right? So you really have to think about this attesting to some program. And this setup always has these three components that are very important. This is a prover, this is a verifier, which are two different parties. And there is this program that is proven, this computation bit. So really, whenever you are working with any ZK system, you should always be able to answer these questions. Who is the prover? Who is the verifier? And what is the program that's been proven? So yeah, the next question is, how do you understand private inputs here? So I said that's there's a computation possibly with private inputs. Maybe somebody already has an intuition here. These are not, yeah?
Private inputs are inputs to the program that the verifier never learns about.
Yeah, exactly. These are the inputs that prover knows, verifier doesn't know, and should not learn. This is exactly what private inputs are. So here is the general flow, how this prover, verifier, and program work together. So the first step is really that prover and verifier should come together and they should agree on what is the program that they're discussing, what is the computation that prover will be proving. I mean, here I'm taking into parentheses the proving system. This could be important, for example, later for trusted setups, we'll see. But here, an example of this program could be computing a SHA-256 hash or computing state root, for example, of blockchain, and we'll see some precise examples, and we will write some precise examples later. So the next step is that a prover has this program that is publicly known. The prover might have some private and public inputs to this program, and the program might produce some public outputs. So prover basically runs the program and generates a proof that this program was run on these inputs and produced this output. So basically the whole algorithm of prover produces this proof. This is the ZK proof that we'll be talking about. And step 3, verifier takes this proof that was produced by the prover. The verifier knows also public inputs, knows the public output. Verifier doesn't know the private input, as we discussed. And then the verifier can check whether this proof is correct using these inputs and outputs, basically producing true or false. So this is the general conceptual flow of ZK proving. And something that usually happens in practice is that there is this prover verifier asymmetry in the setup. So usually the prover has to do a lot of work to produce this proof, but the verifier has to do very little work to check that the proof is correct. Yes?
And the program need to be known for both parties, or only the inputs and outputs?
Yeah, so the question was whether the program needs to be known. Yes, the program needs to be known. This is kind of step 1 of the general flow. Prover and verifier has to agree on the program. It has to be publicly known. Yeah. Yes.
I just read that in Bitcoin was the Google team or whatever proved some quantum stuff. And
yeah.
They did it with ZK, but they did not publish the program. Right?
That's a very good comment. I will be mentioning this later during the workshop. But yeah, basically there was a comment about Google quantum paper that published ZK proof of something, but not the program. Yeah, exactly. I mean, they published the program, they didn't publish the private inputs to the program.
Okay.
Yeah. So yeah, in the further examples that we will see, verifier always has to do very little work. Prover has to crunch a lot of numbers. We will see some benchmarks as well, but yeah, this is the more or less the general way how it works. So this will be my only slide about ZK under the hood. This is more like a footnote of curiosity, but you can explore a bit more on yourself later. But basically how this step works, or this whole process works, is that you have to encode your computation as some polynomials. This could be done in several different ways. This is quite an engineering task. And then you have to cryptographically prove some stuff about these polynomials, basically that you constructed them correctly. And the keywords here are the arithmetization, is the process of taking a program and converting it into polynomials. There are several ways to do this. There are some these keywords that you can search for, Plonk, R, around CS. Yeah, I will leave it as a footnote. Maybe you can look it up on Wikipedia. The question was, what are the polynomials? And the next step is proving some polynomial facts. And this is the polynomial commitment schemes. The keywords are KZG, Fry, sum check, and so on. And when I say encoding computation, this is one example of arithmetic circuits. So this is a simplified way of how you can encode computation. And in this case, it's a very simple computation that can do sums and multiplications between integers.
It's also kind of like a polynomial, but with numbers already.
Yeah, this is a you can basically present polynomial as this type of arithmetic circuit.
And one output.
Yeah, I mean, polynomial is you take some things and you multiply them and sum them together. But this is like one of the examples. I don't want to. Yeah, this was just an illustration of encoding computations. Yeah, just a flavor. So the first example that I want to cover is the ZK rollups. And the reason why I want to cover it is one, because I work for L2Beat. It's basically a project that follows L2s and ZK rollups on Ethereum. You might have seen this website. So there are these blockchains. But the other is that actually ZK rollups and blockchain interest for zero knowledge really produced a lot of theoretical results, a lot of practical results, a lot of tools were created because of this exactly use case. So this is very important for the kind of the history and the whole scheme of zero knowledge. And the idea is it's basically a blockchain problem. So you have here are the fees on Ethereum, and you can see that at some point they spiked to very, very high numbers. You had to spend hundreds of dollars to send a transaction. And the solution that Ethereum came up with was L2s, rollups basically. So you take this computation, you take transactions basically, and you put them onto another blockchain. And then you basically generate a proof that whatever happened on this other blockchain is correct, and this proof is posted on Ethereum. So in this sense, we kind of compress execution. We don't compress the data, but we can outsource executing transactions to another blockchain. And this some examples of projects that do this quite successfully. And maybe a small note here without going too deep is that this particular use case is actually not ZK. So that's why I don't like saying ZK rollups and like saying validity rollups, because usually the transactions on these blockchains are public, so you can see actually what's going on. But this is kind of the name sticks a bit. People say ZK rollups. And I have here a couple of questions for people who know a bit about ZK rollups. I think there should be some in the audience. So here my first question is, what is the program that's been proven in this ZK rollup application?
If we want, we can have a second recording
Yes.
mic. So if you have the answer, you
Okay. Yeah, I mean that's
New coins created.
Yeah, things like that.
yeah, that's
The integrity of the transactions.
exactly. Yeah, Paul, you have
Just,
No, just the microphone.
yeah, just that EVM instructions get processed correctly.
yeah, exactly. So this is a general answer. So that the logic of blockchain is executed correctly. This is the program. Basically, it's like a client program of a blockchain. I mean, depends on the blockchain logic. Yeah, this is the program. So the next question is, do you know who is the verifier in the scheme? Yes? Philip?
I would say it's a smart contract on the layer 1.
Yes, exactly. That's correct. It's verified on right on chain. And do you know who is the prover? Or does anybody know?
Anyone else?
Don't be shy. It's
I think.
yeah.
Smart contract on Ethereum in this case.
No. So it's not the prover.
The layer 2 network itself.
Yeah. So it's the operator of a layer 2 network exactly. So if you operate L2 network, you have to operate the prover, which is usually a big beefy machine that generates the proofs for all the blocks. So yeah, this is just to get you a bit warmed up and also go through this mental model of prover, verifier, and the program. Okay, so the next thing I want to mention are the trusted setups. And yeah, so the trusted setups are a part of many zero-knowledge systems, but not all of them. And basically, some of these proven systems need some secret parameters to work, and this is a part of cryptography that they operate. And this is a secret parameter that if somebody knows, that they can generate whatever proofs, they can forge arbitrary proofs. So this is really something that nobody should know. And I mean, how do we work with them if nobody should know them? This is done by computing these secret parameters in distributed way. So many different entities kind of contribute pieces of the secrets, and they delete the pieces, and then you have kind of this secret that nobody knows. But in principle, if all of the people and this is called a trusted setup, so when people come together and contribute these pieces of random data for this cryptographic secret. And in principle, if everybody who participated in the trusted setup collude, come together and combine all the secret pieces, they will be able to learn the secret, and they will be able to forge any proofs. So in this way, if you have a trusted setup, you kind of have a trust assumption, basically, that all these people who participated in a trusted setup ceremony actually don't decide to break the system. And this is important for your trust assumptions. So some proven systems have one trusted setup per the whole system, so it kind of needs to be run once, and then it can be reused for different programs. But some proven systems.
And this is because if they don't delete it, you can guess this on the curve, or like.
If they don't delete it, then they basically can generate any proof they want. They can prove arbitrary stuff.
Like frost in Bitcoin when you don't delete the keys and rotate them, or like does it have to do with the cryptographic curve, or?
I mean, yes, it does have to do with cryptographic curve, but I mean, this trusted setup is a kind of some secret points on the curve. Yeah.
Okay. Understood.
Right. But what's also important that sometimes you need to generate this. You need to run the ceremony basically for each program separately for Groth 16 systems. So then it's kind of, you have to always keep this in mind when you write your ZK programs, for example. So yeah, here are some examples of trusted setup ceremonies. For example, you can one that's quite known as Aztec Ignition by the Aztec team. It had 176 participants, quite a moderate number. Then there was the big one, Ethereum KZG ceremony for blobs. It had much more participants, but there is also this trusted setup ceremony, for example, by SP1 Growth 16 final wrap that had just 7 participants, and they were all somehow working for the same company. So this is all to say that, you know, there are different trust assumptions that you bring with a trusted setup, and when your goal is to develop a privacy preserving app and you really want to be mindful about your trust assumptions, this is something you also have to keep in mind. So something we have done at L2Beat is develop a trusted setup framework. This is a link to our blog post. So what we do is, I can also show you on the website. This is our website that ranks the different proving systems, and you can see, for example, we rate this one red. You can see a bit more details, or if you're curious about a particular trusted setup, you can go into the detail page, and we have a bit of a description for trusted setups. This one is this Aztec Ignition, so you can see some links and so on. So just a bit to bring a bit visibility to what's going on, but this is something you also should keep in mind.
Why was it red?
It's red because it's just 7 people.
Okay.
Yeah.
Sure. Okay.
Yes?
Is there like a mathematical minimum where I would say statistically this is a nice number?
No. We just, the way we came up with this different tiers is we had a look at what's going on in practice, and we kind of saw what's
Empirical.
basically empirical. Yes, Philip?
So if you have proving systems where you have to do the ceremony once for the whole system or once for every circuit, why would you choose a proving system that you have to do it for every circuit?
Yeah, the question was, why would you ever want to do a proving system where you do the trusted setup per circuit? The reason is that it's the one that has the shortest proof and it's cheapest to verify. Growth 16 is the most kind of efficient in some sense. So you kind of gain a bit of performance. And for example, there is this risk zero verifier that did also run a trusted setup for Growth 16. They managed to basically collect 238 participants, and in the end, kind of if your set of participants is big enough who participated in your ceremony, then my personal opinion is that it's still okay, especially, for example, if you personally participated in it and you know that you deleted your secret share. But yeah, so there are trade-offs.
Is there like some procedure for safe migration of the trusted setup? For example, we understand that the trusted setup might have been compromised. We're not still, like the system is not hacked, but we understand that maybe within 1 year it could happen. So is it possible to regenerate and then?
Yeah, the question was whether it's possible to migrate a trusted setup. So no, I would say in such a case you have to redeploy your system basically from ground up by doing the whole thing.
So like the whole value with all the created proofs would be lost? Because
Yeah, more or less. Oh. Yes?
So this may be more like a remark, but also a little bit like a question. The way I understand it is, if you participated in the ceremony, you can be sure because as long as only one participant deleted their contribution to the ceremony, it's considered safe.
Yes, exactly. If at least one of participants was honest, then the ceremony is honest, because you need all of the shares together to get the secret.
How large the pool was, even if it was like 1 million participants.
Yeah.
Okay. It doesn't diminish the
Yes.
safety.
You just need one honest party, and it will be fine.
But it kind of, if only one is left, like the space for the brute force might be not.
No, it does not affect the space for brute force, because basically, if the contribution was random enough, then you will not be able to guess it. Yeah.
And each contribution, the parameter is like some big number, yeah?
Basically, yes. Yeah. Yeah, it's a big number on an elliptic curve. Okay. Yeah. So this is about trusted setups, and basically when we will be working on the workshop writing some circuits, the proving system there will also have some trusted setups, which we will not touch and we will not see, but you just keep in mind that it will be with the trusted setup. So yeah, the next example I want to cover is already a ZK example with some privacy included. And this is the one that people throw around a lot when they speak about zero-knowledge technology. And this is kind of the general idea, I think is called ZKID. I don't know, maybe who came up with some first designs. I've heard some from Polygon a couple of years ago. But this all comes from this, basically the question of how much info about yourself do you want to reveal. There is a real problem that some platforms get hacked all the time, and the photos of your documents leak all the time. But for example, maybe the platform like Discord only wants to know that you're at least 18 years old. This is the classical example. So this ZKID concept is an example where you basically locally generate a zero-knowledge proof that you have an ID and your age is at least 18 years. And then this proof is generated locally. Your data about your ID never leaves the device. And that's how you kind of achieve privacy. This is the general concept. And to illustrate this, I chose this particular implementation that is, I think, now a part of a Google Wallet. The library is called Longfellow ZK. So this is basically something that's put in production, and I think it's also quite interesting that a big company like Google also looks at this technology. And basically, here is how it works. So, and this pretty much works like this for all ZK ID solutions. So you have some authority. In this case, this guy with the hat is government, for example, and this authority issues the IDs. So when they issue an ID, they have some signing key, they have credentials, and they can sign basically your digital identity or your passport. And with this signature, they basically say that this is a valid ID. So then you as a user maybe have this signed ID and you want to prove to the verifier that you do have an ID and you are at least 18 years old. So maybe this is a Discord on the right. So what you do, you locally, using this data that you got from the government, you generate a zero-knowledge proof of the following things. So you prove that you have this ID validly signed by the government, where basically the private key of the government will be a public input. You also prove that the age of this ID is at least 18. Some other things, for example, you can prove that ID has not expired. It's maybe not on the revoked or some blacklist. And that's it. So you generate this zero-knowledge proof. And the ID data never leaves your device. And you send this proof to the verifier. And when they check this program proof, they basically know that this all holds and that you satisfy these requirements. So this in the whole this thing, by far this bit is the most challenging and the most important, the one of checking the cryptographic validity of ID that it's signed by government, because basically if you don't have some authority that can attest that you do have an ID, then this proof is not basically you cannot prove you can't convince the verifier that you actually do have this ID. And technically also this cryptography part in this first bullet point is the most complicated one in this example. Yes.
Is validation, or I mean, it's valid, can be something that can expire. So
Yes. So I mean, still valid is maybe you pass the current date as the public input as well, and it just checks with the expiry date on the ID. So maybe nothing has to change. But for example, the last item, maybe the government wants to have the option to revoke your ID at any moment. Maybe they are allowed to do this by law. I don't know. But basically, you can also prove that maybe you are not in some dynamic list that is being constantly updated by the government, and this could be a part of the Ziki proof as well.
Okay, but if Discord asks for the proof now, and I have a visa that expire in 3 months, and then Discord doesn't want me because I come from a country that I'm not allowed to use Discord.
I mean, it's all.
In 3 months, he's able to say that I sent a proof that now is not valid anymore, or is using an outdated proof that was based on data that are not valid anymore in the future.
Yeah, so I think in Google, I mean, it all depends on implementation, but I think in Google you can do it like this, that you can actually see that the proof has expired and is not valid anymore. Yeah, you can do this. Basically by providing a public input, like what is the current date, for example. Yes, Philippe?
What are the public inputs, or the inputs that the verifier is using for this particular setup?
Yeah, I mean, that's a good question. I don't know exactly. If I had to guess, I would say, yeah, maybe the authority of the public key of the government, signing authority. Maybe they also say, for example, maybe they can choose among several signing options, like several signature schemes or so. Maybe they can also pass this 18 as a parameter, like maybe somebody says 18, somebody says 21. Probably they also pass the, some information about this revoked list, like a root of a Merkle tree, I would say. Maybe current date as well. I would say then with this information you can check all of this, 4 of these conditions.
Is this like a general purpose library or just for this government ID experiment? We put
This Longfellow ZK, you mean?
Yeah.
I think this is really meant to be an integration into Google Wallet, but you can use it in more general ways. They implement some cryptography as well.
And it's designed to be like local first, not just
Yes. Yeah, exactly. This all happens on your phone, and this is also optimized to be run on phones and low performance hardware. Yeah.
Is the root of the Merkle tree also retroactive, or is it a static thing?
I think you can also update it, like with this revoke list from the government. You can do this. There was also a question.
Does this also mean that the government in this case would have to essentially issue the proofs with the passport itself, or like?
So what they will have to do is they will have to issue signed IDs. So they issue an ID and the digital signature, basically that they attest this ID is correct. And then they give this information to you. And using the signature, you can already prove that you have an ID that was signed by the government.
Okay, so then therefore you could then ask all of the, you can answer all of these questions.
Yeah.
Just by that, okay.
Yes?
So, but then in that scenario, my ID is just a tuple of data, my date of birth, my and it's just signed by this authority.
Exactly. Yeah, the question was if the ID is just a tuple of data, like date of birth, name, and so on, and it's signed by the government. Yes, that's exactly. Yeah. Yeah, so this is one of the implementations. I think there are some other. Yeah.
Sorry, I have another follow-up question. So, but then I can prove that I ran this program with a valid input, but not necessarily that it's my input.
Yeah, I guess so. I guess you can. So maybe an input as well could be your first and last name, which I don't know. Maybe you have to provide some other way. But basically, yeah, this is a. This will have to be solved in some other way, I guess. Yeah, so this is actually my last slide of the first 30 minutes presentation. It's already 45 minutes. But I wanted to say and kind of give a preview of, I think, some other sessions that will be in the program. But my point is that ZK is a part of a privacy stack, but it's not the only technology. As already mentioned, kind of the main feature of ZK is proving some computation, and the main use of ZK for privacy is proving computation over private data locally, where the data never actually leaves your devices. This is the main strength, but there are some other privacy-preserving tech. So MPC, multi-party computation, is the technology where you split the data among several nodes, and they kind of compute something on this without having the full picture. This is exactly what happened in the trusted setup case, where you distribute the shares. This is also used for privacy. One particular example is garbled circuits. This is, for example, implemented by COTI layer 2. There is also fully homomorphic encryption developed by companies like Zama or Phoenix. And the idea is that you compute over encrypted data. So users encrypt their own data. They pass it to some basically servers, and they can compute something over this encrypted data and not learn anything about the data itself. And another technology, so these are cryptographical technologies. Another one is purely hardware, these TEs, trusted execution environments. These are chips that actually now I think most of the phones have. This is a chip that has some parts that are not accessible to other, basically hardware restricted from tampering, and they sometimes have the signing keys, so they can prove that, for example, that some program was run, and they can kind of attest to which exactly program was run. This is the idea, but actually there are many vulnerabilities in trust execution environments recently, so they are hackable and you can extract some information, but yeah, this are also some alternatives that I just want to put this a bit in context, so it's maybe a bit clearer in some next sessions when you learn about this. So I don't know, do you want to make a couple of minutes break? So something I want to cover a bit are the ZK prover architectures. So basically, what I've been explaining before is a bit general, but in practice, how I explain this program kind of needs to be written specifically for each particular use case. You take it, this is usually called ZK circuits, this program. So you write ZK circuits for each particular application. There are several ways why this is actually not such a good developer experience. I mean, basically, we will see that you need different languages, domain-specific languages, to write these circuits. This is the original, how it was done originally. And I mean, usually also, for example, for growth 16, you have to rewriting your program requires a lot of modifications, like a trusted setup, for example, and so on. So I will. This whole problems led to ZK VMs, zero knowledge virtual machines. But maybe first I still want to show what I mean by a bad developer experience. So I will be showing several languages with which you can write different circuits. And so this one is Noir that we'll be touching later on the workshop. This looks actually quite okay, Rust-like. We'll see how it works. There are some, for example, this is an older language called Circom. Already this is maybe not so user-friendly or not so familiar to some people. I don't know what is the syntax. But this is still a good tool for writing circuits. If you know Golang, you can use this Gnark library. This is written by Consensus, the guys who did MetaMask and Linea. This is an example of, this syntax also looks a bit weird for me, but basically this is from Aleo, a language called Leo. So what I want to say with this, maybe one more, this is a Lurk Lisp-like language for writing circuits. Basically what I want to say is that there were so many different languages for writing circuits, and they had not so, you had to learn them. And the idea that people came up with, Starknet was the first, is the idea of zero-knowledge virtual machines, where basically your whole circuit is a program that takes another program as an input, and it just verifies that this this input program works correctly. So you have this single circuit basically, and you plug in the basically the code that you want to prove and verify into it. So this has several developer experience improvements. For example, you can abstract away a bit this zero knowledge circuit part, because it's kind of fixed. You can have more native support for normal programming features like conditional execution loops and so on, which is not super easy in these previous languages. So yeah, one example here would be Cairo, which was kind of the first ZKVM developed by Starknet. I'm just showing how it looks, but it's still a different language. But maybe the biggest step was done when ZKVM languages targeted virtual machine that can be compiled from normal programming languages like Rust. So you can take the pretty much normal Rust code and compile it down to RISC-V, and then this RISC-V will become an input to the ZKVM basically. So this is a nice developer experience. You can also use not only Rust but other languages that compile to this. RISC-V is a quite general architecture for hardware and low-level software, and basically there are several modern and quite advanced zero-knowledge VMs that prove RISC-V programs. Here you can see some examples. Basically this movement is so big that last year there was even a proposal from Vitalik to replace EVM with RISC-V on L1. I think it's not super serious proposal, but it's interesting that it was proposed. Yeah.
So how these things that the program take the program as an input works, and why all these example of language are imperative language and not declarative that can be expressed like data, and basically are just a data structure that is I think more normal to interact with the data structure instead of something that you have to parse and recreate and ask of what the program is, and this concept of virtual machine itself, where you actually can use an algorithm as a tree of data, because that actually is what it is.
Mm-hmm. So yeah, the question is, how do I formulate it? That why kind of bother with putting the program as an input to a VM without, because it's maybe not the most native way to represent computation? Or?
Well, I mean, every programming language at the end things become a data structure. But in the way that imperative programming language works, is a file of text that then can be parsed, and then there are all these operations to translate it in another instruction. While there are other declarative language that are more close, that are basically data itself, or also functional programming language. These together, the program itself is a data structure.
Yeah, so the question about imperative and declarative languages, I don't know too much about this to answer it fully, but I can say that in these ZK circuits and zero-knowledge VMs, the input programs, or basically the programs, really a very low level. So when the proving system works with the program, then it really decompiles it in a very basically low level things. So there you already have a bytecode that is not very structured. It's just a sequence of steps and data. So the nice thing about ZK VMs is that you don't have to work with them differently for different use cases. For example, in our previous examples that we covered, if you have this circuit for Google Wallet, then your input will be you will have to structure your input in a very specific way, passing the your signed ID and so on. And if you have an example with, for example, proving a hash function of some number, you will have to structure it differently. In ZKVM, you have the same structure of input, but basically you put the program and you put inputs, kind of abstracted away, and the prover is fixed and it doesn't change. I don't know if it answers your question. Maybe we can.
So basically, it's a compiler.
So you already passed the compiled program.
My question with declarative language can be an interpreter instead of a compiler.
Okay. Yeah. So this is all compiled. This has to be compiled kind of before. Yes, Philip.
So what are the trade-offs? If I'm using a virtual machine, I assume that it has trade-offs.
Yeah.
Versus a bespoke circuit.
Yeah. So I will maybe go a bit more in details later, but to be quick, the circuits are usually more efficient because VM is a bit more general. VM has a nicer developer experience, and also VMs consume more memory because you have to kind of represent the whole computational trace in memory for proof generation. Maybe Justin also.
Yeah, I wanted to say, like with your points, like another reason that you'd want to use a VM, or maybe you want to write a circuit, is like how much expertise and how much time you have, like from a security perspective, because you can, if you write the circuit yourself, like it's very, very easy to get a little thing wrong, which would be catastrophic. Yeah. But if you use like a ZK VM, like you've offloaded all that risk, because like they're ensuring that all the execution is going to happen like perfectly and everything is properly going to be accounted for. But if you like take that into your own, you know, so it's like the trade-off. Like if you have the cryptographers, if you have the time and the runway to like write the circuit yourself, you'll get that sort of improvement in performance and memory. But like if you don't trust yourself to do that, you can go the ZK VM route and you can still get all like the protection.
I just wanted to get a feeling of what are the trade-offs. Like, is it like 10 times more computationally intense?
Yeah, I will show some benchmarks later, but yeah, now it's shifting. Like there is a lot of development in ZK VMs now, so it's becoming less of a mode, let's say. So here I'm just putting still on the RISC-V topic that just this EthCC conference last 2 weeks ago, Lini announced that they will be transitioning as well to RISC-V, and these guys were developing circuits for 4 years. So I think they're clearly kind of the reasons for using circuits and ZK VMs are shifting. So it's still quite dynamic. Not to go too much into the inner workings, but basically ZK VMs cryptographically are very different from circuits. The proving systems as well. A nice thing about ZKVMs is that usually they do not require trusted setup. This sets them apart from circuits. Then usually they generate proofs faster, so they work faster. But they require much more memory. That could be tough on consumer hardware. And yeah, the proofs for ZKVMs also, you can see approximately 1,000 times bigger or so. Generally, I would say ZKVMs are better better proving technology, but in my kind of workshop, I will still be focusing on circuits, mostly because of the last point. So ZKVMs are still a bit tough to run on, let's say, on phones, on local hardware. So if you are trying to work on some privacy-related application, then circuits are still superior, just because you can realistically run them in browser, you can realistically run them on a phone, and this is not something you can currently do with ZKVMs. Yeah, and this screenshot is about trusted setups that you can also see on the on our website. That there are a couple of proving systems from Starkware that do not use actually a trusted setup, which is unique. So we just wanted to highlight this. So here I try to collect some benchmarks. There are actually a lot of different benchmarks around on internet for different proving systems. So here I try to mainly to track memory requirements. I think the proving time is not super different for circuits and ZKVMs, but here roughly you can see that I mean, you can also have CPU, GPU different acceleration, so it's not very fair to compare. But here you can see Circum and Noir are two circuit-based things, so they can the peak memory is significantly lower than these ones, which are ZKVMs. This is one kind of data point. Another data point, this is all ZKVMs. This is just a general ballpark of how much memory do you need to prove signature verification. So we see DSA signature verification. You see quite a lot of memory, especially for some of the not so optimized ZKVMs. So here is another unrelated data point for proving SHA-256 of this. So this is the size of the input from 64 bytes to 64 kilobytes. These are different circuit-based systems, and this is this was done in I think 2013 or 14, so quite a while ago. 2023. I mean 3 years ago. And to compare, these are the numbers of the same thing proving SHA with ZKVMs, but this is I think later, maybe 2 years later. So it's I think 25. And if you compare, for example, let's say 2 kilobyte inputs, you see here many ZKVMs need around from 5 to 10 gigabytes of memory. And here you can see 2 kilobytes, this as well, somewhere from 1 to 10 gigabytes of memory. So you can see that they're not so different, but from 2023 to 2025, this was kind of a lot of improvements. But yeah, so this is still to say that the benchmarks really depend on proving system, on use case, CPU, GPU. It's very hard to objectively compare systems, but I think this should give you a rough estimate on how much memory, for example, you need to prove something. That's still quite a bit of memory, I would say. Yeah, so maybe I will just quickly say here that another nice thing you can do with the ZKVMs is recursive proving of proofs. And this is an idea when you take a proof generated by a ZKVM and you verify it within another program. So this allows you to, for example, parallelize proving things. You split, for example, proving a block full of transactions. What you can do is you can prove each transaction separately on a separate machine, and then you can take all these proofs and aggregate them together, and kind of the final proof will attest to the correctness of all the previous of all the transactions. So this is one way you can use. Another way you can use is you can wrap one proof into another proof. So if you take, for example, a proof from ZKVM that is usually large, up to 100 kilobytes, you can prove it with a Grot16 system that produces 200 bytes proof, and it's very small, very quick to verify. And maybe this one you verify with the circuit on chain. So again, just to quickly show, you can see this on the ZK catalog. You have this main prover tech stack that usually is a ZKVM. So these are the ZKVMs, and they usually are wrapped into Plonk or Grot16 circuits. So this is what actually happens in production. But so there are a couple of things that you can do if you can verify proofs within proofs. And now pretty much every ZKVM does this thing. So this one last example that I wanted to explain before we go to the workshop part is about semaphore protocol. So this is basically the main idea could be simplified to this anonymous DAO voting. I think it's a bit complicated than this, but maybe this is a nice conceptual way of thinking about. So this is, I will later show that this is actually implemented by privacy team within the Ethereum Foundation, so you can actually use the implementation, but let's maybe... The semaphore, I mean, I think a semaphore implementation uses, some, I don't know if they have special precompiles, but maybe. So the problem is how to anonymously vote in a DAO on chain. So what we have here is that we have users, and users have, let's say, private identities. Well, say self-sovereign identities, let's say, where you have a private key and the public key, and maybe people know your public key, maybe not. It's not so important. And these users form a group, which is like a DAO. It's basically a Merkle tree of public keys that you can add users to or remove users from. So this is like a publicly known group. Then this group also defines, so I'm using the terminology from the protocol. They define scopes, but you should think of them as like proposals. So DAO, for example, creates a proposal to vote on, and then users can send arbitrary messages in a given scope, like for a given proposal, and they can do this only once. For example, vote on an option, and let's see maybe in how this works with members. So here you can see this DAO with 4 members. The keys kind of are on chain, the public keys. This group maybe creates 2 scopes. The first is about some political party. The next one is about where to have a dinner, and what users can do. So users, if users are a part of this group that is managed again as a Merkle tree on chain, they can signal in a particular scope only once. So they write a message, and this kind of signaling appears anonymously in such a way that you cannot connect basically who from this group wrote this, but you see that somebody did. This person was a member of the group, and they cannot signal twice. They cannot. Yeah, I'm coming to this. That's a good question. But maybe important thing to say here is that this protocol doesn't have any handling of Sybil risks. So basically, if your DAO is not filtering out Sybils, then somebody can like join 20 times and vote 20 times from 20 different accounts. But what protocol guarantees is that a single address cannot do this twice. Maybe let's quickly see if somebody can quickly explain what a Merkle tree is, because this will also be relevant for our workshop. So yeah, can somebody quickly say what a Merkle tree is?
Well, it's just a hash that any address can that you can compare to that hash, verify if something is contained to that in a way.
Yeah.
So construction is that the lower level hash 00 is the hash of piece of data L1, hash 01 is the hash of L2, and then there is a hash 0, which is actually the hash of the hashes of hash 00 and hash 01. And you go upwards, and as a result, you can kind of verify different statements in logarithmic time by going.
Yeah. Yeah. So you can verify the. You have this top hash that is the root hash, which is kind of the public piece of data. You also have these elements here in the bottom that who are members of a Merkle tree. It's kind of a set. And then you can prove that somebody is a member against the root by providing sibling hashes and recomputing the top hash from this provided info. So if you want to prove that this guy is in the tree, basically you have to provide this value, then this value, you hash them together, you get this one. Also have to provide this value and you hash together and check that the hash is equivalent to the root. So this is how Merkle tree works. It's just a reminder. So how exactly the question, how do we prevent somebody from voting twice? The answer is actually conceptually the same as how you prevent tokens being spent twice on Zcash, for example, or withdrawn 2 times from some mixer. The idea is called nullifier. This basically, when user signals for a scope, when they vote on some proposal in a DAO, they nullify the possibility of sending this signal again. So this is done by computing basically the nullifier, which is a hash of your private key and the scope ID, the proposal ID.
Is it logical 0, logical OR?
So this symbol is the concatenation. Yeah.
It's
Sorry.
concatenation.
Yeah. This is concatenation. Yes.
Does it have to be? Is it there's like a standard that it's like private key then scope ID?
I think
Or
this
can,
is.
you create like a nullifier by like flipping those.
Yeah. Theoretically, you can create nullifier by flipping these values, but this is how I think how it's defined in the semaphore protocol.
Okay.
Is the nullifier stored or then you do a marker tree of nullifier that are voted and then you check against the root of the marker tree?
Yeah, so this in this protocol, the nullifier also is stored on chain as a part of transaction. Yeah. Philip?
Sorry, I didn't understand. So the hash of the private key concatenated with the scope ID?
Yeah.
But how can the contract, the verifier, verify it?
Yeah.
That it has
Yeah,
been
this is the
provided
next
by
slide.
key?
The next slide. Yeah, the important thing here is that if you know the nullifier, you cannot see who basically produced this nullifier. And this is exactly the answer to your question, how this works. So if a user is a part of the group and they want to signal for a scope, basically vote on a proposal, what they do is they generate the nullifier. As I mentioned, they write a message that they want to send, and then locally using this data, they generate a zero-knowledge proof of several things. So first, they prove that they own a private key such that there is a public key that is included in the Merkle tree. So basically, they prove that they know a private key for a public key in the group. This is first thing. They prove that they are part of the group. Next, they prove that the nullifier is actually generated with this private key. So, okay, so they just cannot take some random data and say that this is a private key. No, they have to prove that this is a private key coming from some public key in the group. And they also prove that basically they have not signaled before. So in this I think in semaphore protocol, I'm not sure, maybe they don't have a tree of nullifiers, which some other protocols do have. But you put nullifier on chain, so there you can already check which ones were used and which ones were not. And you can also generate a zero-knowledge proof that basically with this data you attest to a particular message, so then you cannot tamper with a message of a signal, basically making it a public input. Yeah, so this you locally generate without revealing kind of any information. This is on your device. Then you send this transaction, and verifier learns by verifying the zero-knowledge proof. So they also get the message and they get the nullifier. So they learn that some member of the group signaled for this particular scope. They also know that as long as nullifier hasn't appeared, then it means that this user did not vote for this scope ID, and this basically gives you the property that you can signal only once. So here I give the link to the library. These privacy stewards of Ethereum have an implementation. What they have circuits for local zero-knowledge generation. So this is growth 16 circuits, quite efficient on user hardware. They also have smart contracts, for example, to manage this DAO, this group, adding, removing people, and also I think registering nullifiers and so on. They also have some JavaScript packages to write front ends and CLI tools. And they already have.
Sorry.
Yeah.
Is it much different from Macy, this semaphore?
I think it's not too different as a protocol. I think Macy is doing something very similar. Maybe
it's also WebPC.
Okay. Yeah. Maybe I don't know what the difference is actually. But yeah. So here, if I don't know, they already have some projects using this. Probably many of these are hackathon projects, so maybe not very serious. But yeah, you can check it out. And if you want to implement something like this, you feel free to use this implementation already. And yeah, so here are a couple of links that you can check out later. Maybe I will not spend too much time on this. And yeah, so this is the end of the presentation. I don't know if you have any questions to discuss. Maybe we can discuss later, but I suggest to have another, this time maybe 5-minute break. Take out your laptops if you want to follow the workshop. The workshop link, as I said, the GitHub is in the chat. And yeah.